Good morning, all. Very good morning and welcome to the class. So today we are going to continue with the linked list discussions. Yesterday we have talked of insertion and deletion at position P and some given position, preferably valid position. I am sure you have implemented that. Just to help you for those people who could not do the good coding or those who had some difficulty, I am showing the code, although it was very similar to insert and delete after, and the code was already shown. Still fine. Traverse function same as it is, create function same as it is, not a big issue at all that same. Then comes the insertion code. So insertion at some position equal to 1 means insert at the start, and invalid position. In this code, this is not a good way of doing checking for the invalid position, but some of you could think that I will write a length function. Say this is a length function where I will count how much is the length, and then I will simply check if position is less than equal to 0, that is also invalid, or if the position for insertion is greater than length plus 1, because if length is 5, at 6 position also insertion is allowed, but more than 6 will be invalid. So that could be checked as incorrect. Don't forget to return head in that case also, because in every situation, return must be there. Otherwise, the value to be inserted, and then you have all those statements. If position is 1, the special logic. Otherwise, you have the count, and then you can check the condition. In this case, although you could simply write while count less than position minus 1 also, that could also be correct. But otherwise, I have written this condition also, so that I just know that at the last node, it will take care. In fact, this condition will help me for doing better correctness check without length also. So I say we have used length, but ideally length is not a good solution because we don't maintain length in case of a linked list. So for better coding, I should use it after the corresponding while. This while which we are using, the same while we should be able to, just 1 minute, pause please. So after the while, it will be much useful. You can see here, this condition will be helpful. I'll show that code also. But for those who want to handle only valid situation, forget about the length, forget about this. Do that much. That is also good coding. Those who want to practice more, they should think of doing checking without using length. That code I'll show. So I'm simply going previous and count plus plus and then return head. This code yesterday we have seen. Similarly for the delete also, the same way. Again, position equal to 1 means delete. So length-based checking done, but not a best way of doing. Preferably, it should be done after while-based, and that will be better. So here I have similarly position 1, value being deleted, printed here. So I'm not returning. You could return also if need be. And then again, while count less than position minus 1. If the condition was valid or if the position was valid, only this condition is sufficient, and that will work for valid situations. And then accordingly done, and then choice is given, all that done. Lot of test cases given. So I'm just showing to you those test cases. You can do that for this creation and then traverse and then insertion, deletion, output, etc. Delete, will these cases, all this. If you have only valid cases, these will work. If you are handling invalid also, then you should try these cases also, which I am showing here. And if you have invalid and valid mixture to be tested, maybe these. Most likely these cases should be correct, but there could be some typing mistake. So once you try that, if you find something, you can correct that and let me know also. Better way of coding. So no length to be used, and during insertion itself, I should be able to check for the invalid cases. So this is the code which I'm showing you. Rest everything is same, no length used, but here I have that condition, and in based on that, if count is less than post minus 1, that was always for valid situation, this code will stop, and I say if you don't reach to count, then the position was incorrect. If the position was a 0 or minus 1, first time itself the code will stop, still it will be detected. If position was more than length plus 1, still it will be tested and corrected. So this comment will help you in understanding better. And I have written that comment. I'll show you what lastly it says. Sorry. So if you have seen this code, I say check using code this, not previous error link. And that way you should just see that. So this is one way of doing. And then accordingly, I have done the corresponding check at this particular point of time. Similarly, for the deletion case, I'll say for the deletion also the same kind of a logic will work. And let me just have this. So for deletion also, you have the similar way. I have done this, and incorrect position will be needing this check also to be additionally put. And at this point, once I come out, deletion should be tested via previous arrow link. Remember, in case of insertion, count based check was needed for incorrect, but in this case, previous based check will be needed, because based on count, this will be having certain issue for the last node, etc. But list is of 5 element, and then that case needs to be taken carefully. So ideally saying, this is the way you should always do the checking if you want it for invalid also. But again, I repeat, those who don't understand this need not bother. Your 90% code is correct for valid situations. And even if you are able to implement that correctly by your own, you are doing a good programming. Keep it up. Don't worry about these things. So this is the way I'll stop here and then resume to the discussions for next topic for today. So having said that, now let's go to the today's new topic, where we are going to continue our more understanding of the linked lists. So what until now we have discussed is a linked list, and today we are going to continue and have some more knowledge added. Till now what we had was effectively, it is a sequential access, that is a rule. No random access like in array was possible. So linked list has a property that only sequential access you can do. Till now, what we done was a forward access. Forward meant we could traverse the list in left to right direction. There are certain situations where you might be okay with the sequential access, but you also need a backward traversal. But of course, currently my linked list didn't allow that. But there is provision in linked list for that also. For example, if I say I am at some node, let's say node CURR, insertion after current was easy and we have done. Deletion also similarly. What if I want insertion before current node, some temporary node? How to do that? Insert or delete before this. Till now, based on the linked list, what we have done is we have to start from here. If this is my current node, I have to make a logic, bring your pointers and stop one node before current. Only then insertion will be possible. Because for linking, you need the previous link, via that only possible. This will need a loop and it will become a time complexity based issue, which we don't prefer. So insertion and deletion before just needed meant just before this node I wanted. This can be done in unit time also. And for that, there are certain special provisions which we call as doubly linked list. So till now, whatever linked list we have discussed, that by default, when we said linked list, it means a singly linked list. Singly linked means there is a single link. Doubly linked list means there will be double links. Double links means there is a forward link also, and there is a backward link also. Two links will be maintained. Both links. Meaning, if I have my list like 10, say 15, then 20, and so, let's say, then say I have 5 or 25, whatever you say. Now, this was a singly linked list. By default, linked list word used, we will refer to singly linked list. But doubly linked list mean from every node, you also have the back pointer. And obviously, if this is null, this side, this node also has a back pointer to this null. So one pointer I say is a next pointer, and other pointer I say is a back pointer. So Once I have this list, still only start is maintained. So I can always have the list traversed forward or list traversed backward also using backlink, using back pointer. This traversal will be possible. Of course, I have to reach to the last node and then this traversal will be feasible. But this traversal will also mean insertion before a node via back will be possible because I can reach to the previous node also. Effectively, this means that my node structure gets modified. I have here not just the data and link. Instead of link, I am now using the word next, which goes to the next node. I also have the back pointer, which let's say I name as PACK, back or previous, whatever name you want to give. So now my node structure gets modified to have these two fields, effectively meaning that when you had your 10 data stored, not only 10, this pointer was null. Similarly, this pointer pointed to 15, but 15 had a back pointer which pointed to the previous node. 15's next pointer pointed to 20. 20's back pointer pointed to 15 node. 20's next pointer pointed to 5. 5's back pointer pointed to 20. 5's next pointer is null. And this way I have all this. So every node has 2 pointers. You can see every node has 2 pointers. So this becomes a doubly linked list, or also called in abbreviation DLL. So we can do the same programming which we have done till now. The only change will be, first of all, your node declaration will change. That will have 2 pointers declaration. First change. Secondly, earlier, wherever you have used your link-based updation, wherever you have link-based updation statement, some link was being changed. Whatever link change was there, now you should have there 2 statements. One for forward pointer, that is next pointer, and the second statement will be for the back pointer. Of course, the node from where back pointer will start will be different. Next pointer might be from one node, back pointer could be from some other node, but instead of one statement, you will have always 2 statements. So effectively, we will always have one pair at every place. If you do this, you will never forget to have correct implementation done and there will be no mistake. So wherever you have written one statement, make sure that you always think of both pointers to be updated. So 2 pointer updation will be always the concept wherever you have done earlier 1 pointers updation. Yes, from different nodes, that will be always possible. Let's see that. First of all, type def of your structure. So whatever type def struct node you have done, same syntax, whatever you have written, data, etc. you have written. But now the only change being, earlier you had a struct node star link. Now I will say, I will name them as star next and star back. So instead of link, I'm naming them next, and other I'm naming as back. So symbolically, I show like this or show anywhere, doesn't matter. But yes, it means there are 2 pointers. Sorry. So having said that, this becomes your node structure. Then rest everything is remaining same, start, etc. all remaining same. Let's see how create will change. Your all create logic, all will remain as it is the way you have done earlier, except wherever you have link updated, instead of 1, we will have 2. So you had some initial node, some initial statement, then you had some do while statement. And in this do while, you have written temp arrow link, or I'll say you had written here current arrow link equal to temp. This statement was there. So above that, you had a temp equal to malloc and data saving and etc. etc. Now I say this statement needs to be replaced by a pair. Why? Let's say you had this start node. First node created, you stored 10 here. This is your current also. Let's say you have created a new temp node. In temp node, you have stored whatever data you needed. Earlier, what you have done is temp arrow link equal to current arrow link equal to temp. But now I say this also needs this link to be done. So this statement will be now becoming current arrow next, because instead of link word, I am saying next, equal to temp. But whenever you update next, also think of updating back of other variable, other pointer, other node, that is a temp. So temp arrow back needs to be assigned as current. So that's it. Rest everything remaining same. This link is maintained. Finally, once you came out, you said current arrow link equal to null. So this statement also to be replaced by two statements. Obviously, one becoming current arrow next equal to null. What about second statement? That means effectively this pointer has been made null. Now, back pointer is of this node was already connected, hence this back pointer is not to be touched. I'm making this link, but that guaranteedly means one back link was also needed, which I have forgotten. All other links have been there. In fact, starts back I have never touched. First nodes, because from here, this and this got touched. So the pair of this node is the initial back point. But although I can write here also, but better way of doing that will be that before do itself, I should write start arrow back equal to null. Just before that, so that I don't forget to do it initially itself as soon as start was created. And then, of course, you had current equal to start. So this statement is in pair with this statement, written different places. Rest everything is the pair always existing. Perfect. Nothing else to be done. Rest everything, all return and all statements, everything working perfect. Return, start, etc. All going well. If the list was empty, return null. Everything perfect. Nothing to be changed. Similarly, traverse. Now I'll say traverse will be two functions. One will be, I'll say, traverse forward. Other will be traverse backward. So traverse forward, the void function with proper parameters, same as we have done earlier. The only thing will be, instead of word link, you will use next. That's it. Rest everything is same as earlier. Then comes backward traverse. So of course, this will be also a void. Whatever parameters needed, node start will be passed. Only start is maintained for the linked list. So I don't have a pointer to the last node. But what I need to print that if my list has a 10, 15, 20, 30, 25, I want that somehow I should reach to this node, then using back pointer only, not using front pointer, not using next pointer, not stack, nothing like this. You traverse in this direction and your output should be 25, 30, 20, 15, and 10. Start was here, but I want to print this. The purpose of this traversal primarily will be to check the correctness of back connections. So every time I will be traversing forward, I'll also verify the list by back traversal also, that back linking is okay or not. So that to be verified, I should get this output. If this output to be brought, that means first aim should be bring your start, using start, you have to reach to the last node. So effectively, I need to reach to the last node. How to reach? Almost as good as forward traversal. Instead of forward traversal, one change only, that instead of going up to the null, I will stop at the last node. So I'll say, of course, I will have temp node created and temp node pointer created, rather not node, sorry. So temp equal to start. So node will be, temp pointer will be declared, no malloc done. And now I have to traverse it. No printing to be done. And effectively what I need is temp to be shifted to next. Via next pointer, go to next node. Only thing is, don't go up to null, stop one node before. So while traversal forward, earlier we were writing temp not equal to null, but we don't want to go up to null. We want to stop one node before. That I can say, if a temp arrow next is not equal to null, keep on going. Temp is here, so your temp is starting from first node. Temp arrow not next not equal to null, bring temp here. Not equal to null, bring temp here. Temp arrow next not equal to null, bring temp here. Temp arrow next from 30 not equal to null, temp comes here. Now temp arrow next is null. If it is null, when this statement will stop and I will be out of this loop. Effectively now my temp is ready. Effectively now I have to traverse backward. So again, traverse will mean some while condition, and within that printf of your data, temp arrow data to be printed, and along with the data printing, temp to be changed. Temp equal to temp arrow back. I have to go to the back pointer via this. That's it. Condition almost same as what we were doing in the forward, while temp not equal to null. Again, don't write temp arrow back not equal to null. If you write here temp arrow back equal to null, that will be last node will not get printed. If you write like this will be last node printing will be missed. So you don't do this, you can understand why it will be not printed, because I will reach to the last node. That time its back is null, I will stop there, but this node, so I will reach to the 10. Temp's back is null, loop will be terminated, but by that time printf statement has not executed, 10 has not been printed, so code will stop and I will miss the last value. Yes, now this is almost okay with something remaining. What will be the problem in exceptional situations? 99% time it is okay, but imagine, can it fail? Yes, it can fail for one special situation. So 90% work you have done, just you have to think of some special situation. What if list was empty? List was empty, what will happen? List was empty means start was null. If a start was null, code will crash. Why? You will take a temp equal to start, temp becomes null, and then you write a statement temp not temp arrow next. So this code will crash because temp is null, and via null, if you access any field, rule R6 violated and you are going to crash the code. So you have to handle that situation. Maybe you can simply write, firstly, if a start equal to null, you just stop. Nothing to be done. Traversal is obviously not possible. You could simply say return. So this statement you can write extra, and that way your code will simply be over and the traversal will not crash at all. So traversal is also done. You can easily implement without much of a problem. Then obviously the two more operations. So we always say effectively we need create, traverse, insert, and delete. And best way to start with can be nothing simpler than insert after and delete after a given pointer. Let's say insert after certain node, certain pointer. Means, let's say I have here 10. I have this kind of a linking, 15. I have this kind of a linking, etc., etc. Say I want in between 15 and 20. So I say my current pointer is here. Insert after current node. This is we have done for singly linked list. Step 1 we have done by malloc. That was first step. Step 2, the data which we stored here. Second step. Third step. Earlier what we did was connection like this. Now I will say third step will be in pair 3A and 3B. This step becomes 3A. You should also make this step as 3B. So this is your 3A, this is your 3B. Fourth step, you have done earlier this connection. This was a fourth step. Now this to be in pair, let it be 4A and let this be 4B. So obviously, now your list is ready and connected on the other sides. So simple. The logic is very simple. And if you want to implement, earlier you have already done this taken as a temp. So that statement is perfect. Temp equal to malloc, whatever statement, whatever allocation, etc., etc., typecasting, temp arrow data, that also being properly assigned as you have been doing earlier. No change. Third statement. Earlier you had written temp arrow link to be assigned to the current arrow link. This link. You might require some simplicity. So let's take another variable, temp2. Not necessary, but if I take, I'll just note down temp2 is the pointer to the next node from current. That will make things easier for me because I need a back pointer of temp2 also. So I'll be able to access that. So temp2 equal to current arrow next. Now step 3A. 3A said temp arrow next to be linked. Temp arrow next was linked to current arrow link, that is now temp2. So 3A done. Immediately think of doing the 3B. Temp2 arrow link or arrow back. Temp2 is the node, this back pointer to be linked with TEMP, the new node. So 3 becomes one pair. I have done this part. Similarly, fourth A. Fourth A was current's link or next to be updated. So earlier we have done current arrow link, that is current arrow next to be assigned equal to temp. Now I will have another statement back also. Whose back? Temp's back. So temps back to be updated. Temp back to be given a new address. What is the new address? CURR. Temps arrow back to point to this. So this also becomes a pair and insertion is done. So, okay, for almost all situations, but now think of any special situation where the code might be failing. Just like we said, first node is never going to change, start is never going to change because it is insert after, so that's not a special condition. Last, say insertion after the last node being attempted. That can become a special condition. And we have to verify will it work or not. Insertion after the last node meant your current is this node, let's say 15, and this is the last node. Means this pointer is null. And rest others are existing the way they were without much of a problem. Even if it is first node, after first, not a problem. But if it is last node, current is last node, then what will happen? Step 1, okay, malloc can be done, new malloc done, temp comes here. Step 2, temp's data being saved here, let's say 33, saved here. Step 2, perfect. Step 3a. 3a, so before that I have taken temp2 equal to current arrow next. That will mean temp2 becomes null. Last node doesn't exist after this. So third A, this statement, temp arrow next equal to temp2. So temp arrow next becomes null. Not a problem. Still, this is a valid statement. Null is always in caps to be written, just to remember. So temp arrow null next means this becomes null. Perfect. Not an issue at all. 3B. Temp2 arrow back. Temp2 is a null. Nulls via null, if you try to access a field, code will crash. So I'm going wrong. I have to solve this. How to solve? Simple. Always put an extra if condition. Check. If temp2 is not equal to null, only then this statement to be done. So if I'll say if temp2 not equal to null, then temp2 arrow back will be assigned equal to temp. Otherwise, this statement was going to crash. I didn't allow. Fourth A, current arrow next equal to temp. Current arrow next to be linked like this. Done. Temp arrow back equal to current. Done. And I can see my all list is updated. So fourth A, okay. Fourth B, okay. 3B needed one if. Just change this. Special situation got handled without any problem at all. So my whole code works without much of a difficulty now, and everything is okay. And I can see my all linking is properly done. My next node has been added. So in this case, only 3 links will be updated because last node was not existing. Otherwise, that fourth link was also needed. Similarly, for the delete after, I want delete after current. Same concept. Let's say I am having data at 50. This is 20. Let's say this is 30. Earlier, what I did, I had done connection like this and freed this node by taking a temp pointer. Almost same. One additional change. This link also needs to be updated. So step will change for pair, rest everything remaining same. And then we will think of special situations. So I will say, let's see on next page and solve this problem also. Say, I'm saying now I have some data where I am pointing to current node here. Let's say this is 15. Say this is 20. and this is 30. Currently linked like this. Before this also there is a list. After this there is also a list. So I'm not bothered about that. Earlier what we did, I took temp equal to next node of the current so that I can free. So I could say temp equal to current arrow next. Step 1. Perfect, not an issue. Temp comes here. Then what did I do? In step 2, I changed the temps currents link. I changed currents link. This was my step 2. I will say let it be 2A. 2A will mean current arrow next to be given a new address. What is new address? Temp arrow link or temp arrow next. Earlier also we have written the same thing, but I have to also write to be this link to be updated. How to reach to this node? So for this, maybe I can say I'll take another temp2 for simplicity. I could say temp2 equal to temp arrow next. Temp is this one node. Temp arrow next is the next node. Currently, this link has been disturbed. I have already updated via 2A. So 2A step has been done and 2B is yet to be done. So in 2B, I took temp2 and now this pointer to be updated. 2B. So I will say temp2 arrow back is to be updated. To be assigned what? It should get pointed to current. So this becomes my 2B, the pair for 2 statements. This becomes easy, not a problem at all. Then what is third step? Third step was if I needed a DLL to be used, DLL to be printed or return, whatever you wanted to do, that you will handle. And then you will say free temp. Same step still okay. That will be still okay because the temp is pointing there and memory can be freed. So just instead of 2, we had a pair and rest everything is same. One thing more. In book, you will find slightly different syntax for 2B step. So I'll just explain what you might see. I say 2B step can be equivalently written instead of 2 statements. I can do without temp2 variable also. Temp2 means what? Temp2 means temp arrow next. So temp2B statement can also be written equivalently as temp arrow, let me write clearly, temp arrow next, arrow back equal to current. This is also perfectly okay. It means nothing but this was your 15. This is your current node. This is your temp node. This is 20. Currently, you have already changed this link to go like this. Rest everything is still existing fine. So 2A you have changed. Then you said 2B temp arrow next. This is a temp. Temp arrow next means this node. This node is currently temp arrow next. This is a pointer to the next node having value 30. This pointer is correct valid address. Temp arrow next, arrow back is to be changed and this to be changed to go to current. So temp arrow next, arrow back equal to current is also a valid statement. So effectively what I have done is instead of a temp2 word, I write temp arrow next. So this I can equivalently write here temp arrow next arrow back. Even if you don't put brackets, still it will be correct because the associativity of arrow operator will take care to work left to right automatically, and this statement will be perfect. So your choice. Taking temp 2 extra doesn't make any loss. So you can take temp 2 also. That also will be okay. No loss, no problem at all. No extra efficiency loss. So no loss in anything. You can safely do that if that makes you to understand easy. The purpose of talking this is in book you might see this syntax. Again, 80-90% time, okay, because all things work well. After deletion, after first node will also work because start will never get changed. Any special condition. Deletion towards the last end means, let's say the current was second last pointer. Second last node means after this only one node was present, means current is a 15. After this, the node to be deleted is obviously 20, linked like this, but 20 has no extra link after that. Whether we will have the correct code working or not, let's check that. Temp equal to current arrow next, first step, no problem. Temp equal to current arrow next means temp comes here, perfect. Step 2A, current arrow next to be changed. Current arrow next gets changed to point to temp arrow next. Temp arrow next is null. So this effectively becomes null. Perfectly fine, because I want actually this itself. After 20 will be deleted, this should become null. Perfect. 2B. Whether you write temp 2, effectively temp 2 will be null now, because temp 2 means a temp arrow next. So temp 2 will be null. Via null, if you access back pointer via null, it will crash. Temp arrow next is null. Via null, if you access this, it will crash. Hence, 2B will be incorrect. So what to do? Write an if. If temp arrow next not equal to null, only then this statement to be written. If it is not equal to null, then temp arrow next arrow back is valid, and I can assign this equal to whatever I was writing, current. That should be perfect, not an issue at all. I can still write without much of a difficulty. And then your step 3, perfect, fine. Temp was pointing to the node being deleted, del val, return, and free, etc. All will be okay. So this also works without any problem. So effectively, my programming and all that is perfectly done, and special condition also handled. So this special condition will need one extra if to be done, and that's over. So I think now it's the time to wind up. So just the way we have done, now we can have extra work also, that we will be able to do insert and delete before also. And that was the advantage of doubly linked list. Insert before or delete before will be easily possible in unit time. No loop needed. That's the advantage. How to do? Simple. Let's say this is my current node, and I want to insert before. This is a 10. This is, let's say, 15, and you want to insert in between, let's say, value 44. So what I will do? Malloc course temp, first step. Second step, this data, no change. Third step, I can have extra variable temp2 taken if you need, but I am going to have this linking done. 3a to be linked like this, 3b to be linked like this. And you still have these links available, so you can easily go to the back. So previous node, you could take temp2 if you need, and using temp2, currents back was your temp2. So temp2 could be current back, and now you have your third step ready. So you could do 3a and 3b. This is your back pointer, this is your forward pointer. Similarly, you can have this forward pointer and this back pointer as 4a and 4b. And that you can handle. So step 1, step 2, step 3a and 3b, step 4a and 4b in the similar manner. Then think of a special situation, special condition, special situation. In this case, it doesn't mean the last node, obviously, because it is before. So it means insert before first node. If insert before first node, you will have a special condition, null, etc. to be taken care. Along with this, so you will need extra if, perfectly fine. Plus you will need updated start to be changed. Return updated start. So this will be additional change. Hence your function cannot be void anymore. This has to return updated start because start might change. So you will be able to handle special situation. And similarly for the delete before, there also start might change. Because if you are doing the special condition of deleting just before the second node, means the first node was being deleted, then special situation needs to be handled. And for that also, return statement will also become compulsory along with if. So whatever extra if you will write, that will also be done, and do this. I think this much is good enough for you to tell and practice. So I will stop here and give you homework to try all this. So I will say implement DLL doubly linked list and its all operations using repeated choices for the operations. What operations? Same the way you have done, but now I can have special operations. For example, create, of course. Then I will say 2, I will say traverse forward and traverse backward also to be one operation. Always check after every create, insert, delete. Always check traverse forward as well as a traverse backward. Must check that. Fourth operation, insert after a given val, say valid value. And 5 can be delete after a given val, which we have just discussed. So reach to the given val, assume this to be always a valid value. Then 6 can be insert at begin, or maybe insert before a given val. So reach to that pointer, reach to that variable. And the 7th can be delete before a given val. So val is always valid, and 8th to be exit. Val always exists into the list. you can assume this. So you assume this and practice this. Implement this. It will give you a lot of confidence, and I'm sure after this you will find no problem in your doubly linked list or linked list related logics. Try this. If you find any problem, next video will help you in understanding this. Bye-bye. All the best to all of you.